All right, let's look at a series circuit and then a parallel circuit, and we're going to compare multisim to the breadboarding. And what we're going to do in class tomorrow is you will actually build a combination series and parallel circuit and get all the measurements. And then we're going to be done with the breadboarding, at least simple resistor circuits for the time being. This one is the circuit. I just kind of made this up, but I did it so I can get the values. I have 6 volts. And I have a 100 ohm resistor, 200 ohm resistor, 300 ohm resistor all in series. And I did this one so I can work with the numbers easily. If I add up the total resistance in a series circuit, is just adding those numbers up. So I have 600 ohms. And if I use Ohm's law and divide 6 volts by 600 ohms, I should get 0.01 amps, or 10 milliamps should be my current. And in a series circuit, all of the spots in the circuit have the same current, but the voltage across each of the resistors is different, and it's proportional according to Ohm's law to the resistance that it has. So what I can do is I can measure the current in here, and I'm going to use the components that we have. I'm going to use those components that we have in the indicator group. So I'm going to put an amp meter in. And remember, the thing about an amp meter is it's got to replace one of the wires in your circuit. Remember, between the positive and negative terminals, there's a wire inside that amp meter. So if I put it around a resistor, for example, the way I would a voltmeter, and I'll go ahead and place a voltmeter in there as well, then what you essentially do is you bypass that resistor. And that's not what you want to do. So I'm going to put the voltmeter in here, and we'll get a measure across here. The voltage goes across the component. The meter is in parallel with whatever measurement you're trying to make. The current meter, the amp meter, needs to be in series with it. It needs to be in line, and like I said, just replace your wire with your meter. Use your meter as one of the wires. So now when I turn this on, I'm going to get 10 milliamps for my current. I get 10 milliamps of current, and across resistor 2, I'm going to get 2 volts a voltage drop. And if I were to apply Ohm's law and multiply 200 ohms times 0.01 amps, I would get 2 volts for the answer for that. So that's what happens here. The next thing that I want to show you is my analogy of this being a roller coaster, where if we start out with the voltage at 0 and it goes through the battery equivalent to going up the hill, and then it has a 6 volts potential energy here, and every resistor that we go through decreases its potential energy. It decreases the resistance at some point. And so I'm going to put these are little probes that are just going to give me current and voltage around the circuit at different places before and after each of my resistors. And now if I run my simulation, you can see we start out and we get to 6 volts, and when we go through the first resistor right there, it says 6 volts. When we go through the first resistor, then it drops down to 5 volts. And then we go through the second resistor, because it dropped off 1 volt. 100 times 0.01 milliamp, or 0.01 amps would give me 5 volts. We already knew it dropped 2 volts across here, so it goes from 5 down to 3 across the R2, and then finally across what's marked here as R1, the 300 ohm resistor. It goes, the final 3 voltages, final 3 volts get burned off, if you will. And we drop back down to 0 volts when we come back around to the beginning of the battery. So now then, let's take a look at what that's going to look like with a breadboarded circuit. So then what I have here is the same circuit, but I put it on the breadboard. If you watch the breadboarding video, and that's part of the reason I want to redo this one, all of these that are along this red line, all of these holes are connected together. There's metal pins down there, so anything I put on this red line is going to essentially be like I'd connected it with a wire. All of these groups of 5 are connected together, and so anything I put into any 2 of these is going to be as if I'd connected them together with a wire. So what I've built is my circuit. I go from the positive into here, comes into this for everything on this line, and there's only one thing is that resistor has there, is on that line, and I go through the 100 ohm resistor. And then I'm going to go through here, and because these 2 are in that same group of 5, it's connected to the 200 ohm resistor, which is then in the same group of 5 with the 300 ohm resistor, which is going back to ground. So my circuit is complete, And I can show you, I can measure the current, the voltage, by just placing the leads across there, and sure enough, my 100 ohm resistor is about 1 volt. My 200 ohm resistor, if I can get my fingers out of the way, is about 2 volts. And my 300 ohm resistor, I'm measuring across it, like I said, it's just in parallel. I'm measuring across the resistor because I need to find the difference between this terminal and this terminal, the voltage, the potential energy difference. Now the problem is going to be measuring current, and as I said, it's got to be in line with the circuit. So if you've noticed, what we did in the beginning was in the multisim version, I took the wire out essentially, that's a little bitty wire right in there, and I connected using my meter to use it as one of the wires. So the way I'm going to do that is I'm going to disconnect the resistor, and I'm just going to stick it in a random hole over here that's not connected to anything else. And I'm also going to leave my current or my voltage source pushed a little bit out. You can't see that very well from the picture, but what I'm going to do is leave it out so I can get a lead on it. And I know that I needed it to be 10 milliamps, so I need to select the minimum of 10 milliamps. 2 milliamps is too small, so I'm going to go up to 10. And now I have no current flowing through here. Actually, I can go back. If I check this for voltage, I'm going to get 0 volts because I have no current flowing. I'm not connected anymore. So now if I use this to connect my positive side of the battery to the first resistor, then I should be able to see that I'm going to get 10 milliamps, or right about 10 milliamps. Now it's negative because I had the leads backwards. It's really easy to fix. I just switch my left and right hands and put them back down there, and the negative went away and it became a positive. I'm reading 9.7 thereabouts. It's going to change some because I'm losing connection on it. That's how you would work with a series circuit. So the next thing we want to do is look at how to deal with a parallel circuit. First of all, in the parallel circuit, the voltages are the same everywhere. Let me go back and kind of stick these probes into different spots like I did before. And what you'll find is that the voltages across each of the resistors is the same everywhere. It's the current that now changes depending on which part of the circuit you're looking at. So now if I run this simulation and just look at what the probes are, you'll see all of the ones before any of the resistors have a 6 volt potential energy to them. My total current is 110 milliamps if you look at this, and all of the probes after the resistors are all reading 0 volts, and each one of them is reading a different resistance value. So that was just a way to kind of see the idea between the current changes in a parallel circuit where the voltage on a series circuit. So with this one, what I'm going to do is I'm going to break a line and put my amp meter in here. I'm going to place my amp meter in here, and the big difference is, actually, I should have put a vertical amp meter in. It's going to fit better. The big difference is it's more complicated with this. I'm going to delete these other wires because I'm going to put meters in place of them as well. Copy this one, paste it in there, connect that. I'll stop with 2. The third one's going to be the same way. And none of these are my total current. Remember, they were different on each one of these lines. And so if I want to do my total current, I need a meter that's right here. So let me go. Let's put a meter in place right there. And you can see, hopefully, that this one's going to give us the total current because everything in the circuit is flowing through this first meter. And then this one, for example, by U1, is only getting the current that's flowing through U3. And the one U2 is only getting the current flowing through U2. So now if I turn these on, I'm going to get 110 milliamps total, or 0.11 amps. And we get 0.06 amps flowing through the 100 ohm resistor. We get 0.03 amps or 30 milliamps flowing through the 200 ohm resistor. And we should get a very small amount flowing through the 300 ohm resistor because it's the most resistance and it's the most resistant to the current flowing. So now let's look at what that's going to look like on the breadboard. So now we have my meter here and I have my system powered up. Again, I have this set up so that all of the positives are connected to these resistors, and I have the same 3 resistors I had before. And the negatives, I could literally take a resistor, unpower the system for a moment, and I could actually put it in here across my positive and negative rails like this. And if I had this connected to ground, that would actually give me parallel circuits if I put all the resistors in that way, because it's all the positives are connected together, all the negatives or all the grounds are connected together. Since I wanted a little bit of room to work with this, and I've seen some of you have done this, I've kind of chosen to do it this way, where we've got all the positives are here. I sort of made my own bus by connecting these different groups of 5 together, and that's the power of the breadboard, is I can use that to make connections between different groups. So I'm going to turn it on here and I'm going to measure the voltage, and sure enough I'm going to get 6 volts across every one of my resistors regardless of the resistance, and I had the same 3 different resistance values I had before. The problem comes in measuring current. It becomes a little more difficult. Total current is easy. I need to measure 110 milliamps, so I need it again set to measure at least 110 milliamps. I'm just going to take my main wire out and I'm going to put it in here where I can kind of get to it. And again, I want my amp meter to be the wire that connects it to the rest of the resistors. And so once I do this, sure enough, I get almost exactly 110 milliamps. So there's one. That gets me the total. The individual ones are a little more challenging because what you have to do is you have to make sure that your current goes through from your source through the amp meter to your resistor. So what you're going to do is you're going to pull each one of the resistors out. And again, it makes it easier if you'll put it in a hole that's not connected to anything else. And I'm going to put the meter here across. I still have all of the current flowing down this rail to the other resistors. This one is not in the circuit until I connect it with the amp meter, and I find my 60 milliamps there. I can connect this one back and do the same thing for the second one. That was my 100 ohm resistor. This, I believe, is my 200 ohm resistor. Just need to make sure you're connecting those together so that the current goes through the meter. It becomes one of the wires in your circuit. And again, never mess with your circuit with the power on, despite the fact that you just saw me do that. So what we're going to do, as I said in class, is we will take a combination, parallel, and series circuit, and we'll analyze that by hand. We'll analyze it in multisim, and we'll analyze it using the breadboard, so we'll make sure everybody knows how to use the breadboard and take current measurements.